Put simply, functions are rules or equations that define the relationship between one variable and another. Functions are expressed as y equals f of x. In this form, x is referred to as the independent variable, whereas y is referred to as the dependent variable. On a set of axes, we place the independent variable on the horizontal axis and the dependent variable on the vertical axis. Consider this function, which represents velocity as a function of time. Here, time is the independent variable and velocity is the dependent variable. This setup indicates our interest in observing how velocity changes with respect to time, not vice versa. While it is possible to use this function to determine the time at which a specific velocity occurs, it is important to note that velocity does not drive the change in time. This function is therefore represented as vt. Now we move on to another important aspect of functions, the range. The range of a function is defined as the set of all possible values y can take and is usually given as an inequality. For example, for the graph of y equals x squared, the graph never goes below the x-axis, which means that the function's output is always greater than 0. Sometimes there may be no constriction on the range of a function, like this one here, y equals x. When the range of a function is unconstricted, we say the function of x is defined over all real values. We now move on to the domain, which is similar to the range, but focuses on the x-axis rather than the y-axis. The domain of a function is the set of all possible values that the independent variable x can take. For this function, there is no apparent limit on the values that y equals x can take. Therefore, the domain of x is defined as all real numbers. Now consider the function f of x equals the square root of x. The domain of this function includes only non-negative values, as the square root of a negative number is not defined in the set of real numbers. Thus, the domain is x greater than or equal to 0. In this section, we will examine common domain and range restrictions for various types of functions. First, consider a function that is the quotient of two functions. Since division by 0 is undefined, the denominator cannot equal 0. For example, in the function x squared plus 5x divided by x minus 3, then x minus 3 cannot equal 0. Therefore, the domain of this function is all real numbers except x equals 3. The next type to consider is the domain and range of the square root of a function. Earlier, we saw that the domain of a square-rooted function was for all values of x greater than or equal to 0. By extension, the range is also greater than or equal to 0, as the function never passes below the x-axis. To explore this, consider the following function. To find the domain, we know that the function in the root should only accept values greater than 0. This means that the x values must be greater than 2. Additionally, the output of this function will be all positive values greater than or equal to 0. The final common function we will consider here is the logarithmic function. Most students may not have encountered this function yet. To simplify, a logarithmic function can only take values greater than 0, similar to the square root function we discussed previously. An example of this could be the function log x plus 5. Since the input of the logarithmic function must be greater than 0, the domain must be x is greater than -5. In the final part of this video, we will review how to find the intercepts of a function with the axes. To locate where the function intersects the x-axis, we set y equals 0. To find the y-intercept, we set x equals 0. Alternatively, we can identify the y-intercept by examining the function's constant term, similar to how it appears in the equation y equals mx plus c.